Picture this. You're sitting on your couch. Your phone is in your hand. You hit play on a video and it loads instantly. No wire connects your phone to anything. The signal travels through your wall, through the drywall, through the insulation, through the wood studs, and into your device, all in less than a second. You don't think about it. Nobody does. But the reason it works at all is one of the strangest stories in the history of science. It starts with a Scottish mathematician who covered his office walls with equations in 1865. It passes through a German physicist who discovered something so strange in 1900 that he reportedly said he wished he had never thought of it. And it ends in your living room with a wave you cannot see, cannot feel, and cannot stop with your bare hands. This is not magic. This is quantum physics. And once you understand what is actually happening inside your walls, you will never look at your Wi-Fi router the same way again. Let's slow down and build this from the ground up. Because before you can understand why your signal passes through a wall, you need to understand what a signal actually is. Everything you experience as light, heat, radio, Wi-Fi, or color is part of the same family. Scientists call this family the electromagnetic spectrum. The word electromagnetic comes from two forces that are tightly linked, electricity and magnetism. When an electric charge moves, it creates a magnetic field. When a magnetic field changes, it creates an electric field. These two forces chase each other through space in a wave pattern, traveling at roughly 300 million meters per second. That speed is the speed of light. Radio waves, Wi-Fi signals, visible light, X-rays, gamma rays, they are all the same kind of wave. The only difference between them is how long the wave is. Scientists call this the wavelength. A typical Wi-Fi signal running on the 2.4 gigahertz band has a wavelength of about 12 centimeters. That is about the width of a standard piece of paper held landscape. A wave of visible red light has a wavelength of about 700 nanometers. That is roughly 1/10,000th of a millimeter. Both are electromagnetic waves. One you can see, one you cannot. The reason has nothing to do with size and everything to do with how our eyes are built. Now here is where the quantum story begins. In 1865, a Scottish physicist named James Clerk Maxwell published a set of equations that described the behavior of electric and magnetic fields. Maxwell's equations, as they came to be called, predicted that electromagnetic waves must exist and must travel at the speed of light. They also predicted that light itself was an electromagnetic wave. This was one of the greatest discoveries in physics. But Maxwell's equations described waves, continuous, smooth, spreading waves, like ripples on a pond. And for about 35 years, scientists assumed that was the complete picture. Then, in 1900, a German physicist named Max Planck was trying to solve a problem that had been bothering scientists for years. The problem was called the ultraviolet catastrophe. When you heat a piece of metal until it glows, it gives off light. The color of the light changes as the temperature changes. A dim red glow at lower temperatures. A bright white or blue-white glow at much higher temperatures. Classical physics, using Maxwell's wave equations, predicted that a hot object should give off infinite amounts of energy at short wavelengths. Infinite? That obviously does not happen. Something was wrong. Planck found a mathematical fix. He assumed that energy was not continuous. Instead, it came in tiny, fixed packets. He called these packets quanta. 1 quantum, 2 quanta. You cannot have half a quantum any more than you can have half a coin. The energy of each quantum depended on the frequency of the light. Higher frequency meant higher energy per quantum. This was not a physical theory Planck believed in. He called it a mathematical trick. He did not think energy was actually packaged this way. He just needed the math to work. But then, in 1905, a 26-year-old patent clerk named Albert Einstein took Planck's idea seriously. Einstein was trying to explain something called the photoelectric effect. When you shine light on certain metals, the metal releases electrons. Electrons are tiny negatively charged particles that orbit the nucleus of an atom. The strange thing was this. If you used low-frequency light, no electrons came out, no matter how bright the light was. But if you used high-frequency light, electrons popped out immediately, even if the light was dim. Einstein explained this by saying that light actually came in packets of energy, real packets. Each packet carried energy equal to Planck's constant multiplied by the frequency of the light. Einstein called these packets light quanta. Today, we call them photons. The photoelectric effect could only be explained if light behaved as a particle, not a wave. But we already knew light behaved as a wave. Maxwell proved it. Interference patterns proved it. Refraction proved it. So which was it? A wave or a particle? The answer, which took decades to fully develop, is both, and neither. And this is not a riddle, it is a fact of reality. If you want to talk about whether Wi-Fi reaches you, subscribe so you never miss a documented science story like this one. Comment what city you are tuning in from right now. This script is built from verified physics, drawing on the work recorded in the collected papers of James Clerk Maxwell published by Cambridge University Press, and the Nobel Prize lecture of Albert Einstein from 1921, which which you can read directly from the Nobel Foundation archives. Now back to the physics. The idea that something can be both a wave and a particle broke physics. Scientists in the early 20th century spent decades trying to figure out what this actually meant. In 1924, a French physicist named Louis de Broglie proposed that if light could behave like a particle, then particles like electrons could behave like waves. His doctoral thesis, submitted at the University of Paris, was so strange that the committee sent it to Einstein before they would approve it. Einstein said de Broglie had lifted a corner of the Great Veil. De Broglie won the Nobel Prize in Physics in 1929. The proof that electrons actually do behave as waves came from an experiment in 1927 by Clinton Davison and Lester Germer at Bell Telephone Laboratories in New York. They fired electrons at a crystal of nickel and watched interference patterns form. Interference is a wave behavior. Particles do not do it, but electrons did. The wave nature of matter was real. This entire framework became quantum mechanics. The rules of quantum mechanics are radically different from anything you experience in daily life. In quantum mechanics, a particle does not have a definite position until you measure it. Before measurement, it exists as a cloud of probability. It is not hidden in one spot that you just do not know. It genuinely has no fixed location. When you measure it, the probability cloud collapses and you get a definite answer. This behavior was described mathematically by Erwin Schrödinger in 1926 with what became known as the Schrödinger equation. The equation tells you how the probability cloud, called the wave function, evolves over time. Now here is the bridge to your Wi-Fi. Your Wi-Fi router sends out electromagnetic waves. These waves are photons, and photons follow the rules of quantum mechanics. But at the scale of Wi-Fi waves, with wavelengths of 12 centimeters or about 5 centimeters for the 5 gigahertz band, you're dealing with enormous numbers of photons acting together. The quantum behavior averages out into something that looks smooth and wave-like. This is why you do not normally need quantum mechanics to explain Wi-Fi. You can explain most of it with classical wave physics, which is Maxwell's equations. But quantum mechanics is the foundation underneath. It is why photons exist at all, and it is why materials interact with light in the specific ways they do. So why does a Wi-Fi signal go through your wall when visible light does not? The answer lives in how atoms absorb and emit light. Every atom has a set of allowed energy levels. These levels are fixed, specific. They are not a continuous range. You can think of them like the rungs of a ladder. An electron can sit on a rung. It cannot sit between rungs. When a photon hits an atom, one of three things can happen. First, if the photon's energy matches exactly the gap between two energy levels, the electron absorbs the photon and jumps up to a higher rung. The photon is gone. It has been absorbed. Second, if the photon's energy does not match any gap in the atom, the photon passes through without interacting at all. The atom is transparent to that photon. Third, there are more complex interactions involving reflection and scattering, but absorption and transmission are the key ones here. Now apply this to your wall. Your drywall is made primarily of gypsum, which is calcium sulfate dihydrate. The molecules in gypsum have energy levels that correspond to certain frequencies. Visible light, with frequencies of roughly 400 to 700 terahertz, has enough energy per photon to interact with the electron clouds in gypsum. It gets scattered and absorbed. That is why you cannot see through your wall. The paint on the wall has its own pigment molecules with their own absorption properties. Visible light hits them, some frequencies are absorbed, some are reflected, and the reflected ones are what your eye detects as color. Wi-Fi on the 2.4 gigahertz band runs at 2.4 billion cycles per second. That is 2.4 gigahertz. The energy per photon at this frequency is roughly 10 millionths of an electron volt. An electron volt is a unit of energy. 1 electron volt is the energy gained by a single electron moving through a voltage difference of 1 volt. The energy gap that a visible light photon carries is around 1.5 to 3 electron volts. Wi-Fi photons carry about 100,000 times less energy than visible light photons. The electrons in gypsum, in wood, in drywall, and most common building materials have energy levels that simply do not match Wi-Fi photon energies. The Wi-Fi photons slide through without being absorbed. They pass ghost-like through the material. This is not because they are small. The wavelength of a Wi-Fi signal is actually much larger than the wavelength of visible light. It is because the energy per photon is far too low to trigger electron transitions in common materials. The atoms in your wall are effectively invisible to Wi-Fi photons. The photons sail through, but not all materials ignore Wi-Fi. Metal does not let Wi-Fi through, and the reason is the same quantum logic, applied differently. In a metal like copper or aluminum, the outer electrons of the atoms are not tightly bound to individual atoms. They form a sea of free electrons, shared across the whole metal. These free electrons can absorb photons across a very wide range of frequencies, including Wi-Fi frequencies. When Wi-Fi photons hit a metal surface, the free electrons absorb them almost instantly. The energy is immediately re-emitted, creating a reflected wave. This is why metal reflects radio waves. and it is why putting your router inside a metal cabinet will destroy your signal. Your Wi-Fi hits the metal, gets reflected, and bounces around inside the cabinet. Almost none of it escapes. This is also why your microwave oven's metal door, which has those small holes in it, blocks the microwave radiation inside, while letting visible light through. The holes are smaller than the microwave wavelengths, roughly 12 centimeters, so the waves cannot pass through. But they are large enough for visible light photons, which have wavelengths shorter than a nanometer, to pass freely. Size matters when it matches the wave. Water also absorbs Wi-Fi. The 2.4 gigahertz frequency is particularly absorbed by liquid water molecules. This is not a coincidence. Your microwave oven runs at the same frequency range. The microwave heats food because the water molecules in the food absorb photons at that frequency. Their rotational energy levels match. The absorbed energy causes the molecules to rotate faster, which is what we experience as heat. This means that a wall with wet insulation, or a building soaked after rain, attenuates a Wi-Fi signal more than the same wall when dry. It also means that human bodies, which are roughly 60% water by weight in an adult, absorb Wi-Fi photons. If you stand directly between a router and your device, you slightly weaken the signal. Not a lot, but measurably. This was confirmed in measurements published by the IEEE, the Institute of Electrical and Electronics Engineers, in studies on human body shadowing and wireless networks conducted in the early 2000s. Subscribe if you want more documented science stories that connect the invisible world to everyday life. Drop your city in the comments. Now back to the physics. Now let's talk about something stranger. Quantum tunneling. In classical physics, if a wave or particle does not have enough energy to cross a barrier, it does not cross the barrier. Full stop. A ball rolling up a hill without enough speed will stop and roll back. That is the rule in the world you can see and touch. But in quantum mechanics, particles can cross barriers even without enough energy. This is called quantum tunneling, and it is not a theoretical trick. It is a measured, applied, engineered phenomenon. Here's how it works. In quantum mechanics, a particle is described by a wave function. The wave function gives you the probability of finding the particle at any location. When the wave function hits a barrier, it does not drop to zero immediately. It decays exponentially into the barrier. If the barrier is thin enough, the wave function does not fully decay before reaching the other side. On the other side, the wave function picks up again. The particle has a non-zero probability of being found on the other side of the barrier, even though it did not have enough energy to classically pass through it. It tunneled. Quantum tunneling is not just a lab curiosity. The sun runs on it. At the core of the sun, hydrogen nuclei fuse together to release energy. But hydrogen nuclei are positively charged. Like charges repel. At the temperatures in the sun's core, roughly 15 million degrees Celsius, the nuclei are moving fast, but not fast enough to classically overcome their mutual repulsion and get close enough to fuse. They tunnel. The probability of tunneling at any given collision is extremely small. But there are roughly 10 to the power of 57 hydrogen atoms in the sun. The sheer number makes tunneling happen constantly. Without quantum tunneling, the sun would not shine. Without the sun, there would be no life on Earth. Quantum tunneling is also the operating principle behind the scanning tunneling microscope, invented by Gerd Binnig and Heinrich Rohrer at IBM's Zurich Research Laboratory in 1981. They won the Nobel Prize in Physics in 1986 for this work. The scanning tunneling microscope holds a metal tip so close to a conducting surface that electrons tunnel between the tip and the surface. By measuring the tunneling current, the microscope can map the position of individual atoms. The first images of a silicon surface showing individual atoms arranged in their crystal pattern were produced in 1983. The scanning tunneling microscope can image surfaces with resolution better than 1/10 of a nanometer. Quantum tunneling is also at work in your computer chips. Modern transistors, the basic switching elements of all digital computing, are built at scales so small that quantum tunneling becomes a limiting factor. As of 2023, leading semiconductor manufacturers were producing transistors with gate lengths of 3 nanometers. At this scale, electrons can tunnel through the insulating layers that are supposed to stop them. This causes leakage current, wasted power, and limits to further miniaturization. Managing quantum tunneling is one of the central engineering challenges of the modern semiconductor industry. But tunneling is not how Wi-Fi gets through your walls. That is a different mechanism, as we established. Tunneling is relevant to the devices that receive and process your Wi-Fi signal. The transistors in your router and in your phone operate partly under quantum mechanical rules. The semiconductor physics that makes them work is fundamentally quantum in nature. Let's bring this back to the router and follow the signal from start to finish. Your router receives data from your internet service provider. It comes in through a cable. Inside the router is a processor running on silicon chips. Silicon is a semiconductor. A semiconductor is a material that is not quite a conductor like metal and not quite an insulator like glass. Silicon sits in between. The useful thing about silicon is that you can control its electrical properties precisely by adding tiny amounts of impurities in a process called doping. Adding phosphorus atoms gives you extra electrons. Adding boron atoms gives you gaps where electrons are missing, which physicists call holes. Electrons and holes flow under an applied voltage. The flow of electrons is electric current. Transistors made from doped silicon can amplify signals or switch between on and off states. A modern processor contains billions of transistors. These switches, operating billions of times per second to process your data. They are working at speeds that were science fiction 60 years ago. The data, once processed, goes to a radio transmitter. The transmitter generates an oscillating electrical signal at the Wi-Fi frequency. 2.4 gigahertz means the signal oscillates 2.4 billion times per second. This oscillating electrical signal drives an antenna. An antenna converts the oscillating electrical current into a propagating electromagnetic wave. Electrons accelerating back and forth in the antenna generate photons that radiate outward. Maxwell's equations describe this. The photons propagate through the air, through the wall, through the next room, and reach your phone's antenna. Your phone's antenna captures some of the incoming electromagnetic wave, converts it back to an oscillating electrical current, feeds it into a receiver, which amplifies and decodes it back into the data that becomes your video, your email, your web page. This whole process happens billions of times per second per device, and the quantum rules underpin every single step. The energy levels of silicon atoms determine why transistors work. The photon nature of the electromagnetic field determines why the signal propagates. The wave nature of photons determines why the signal spreads in all directions and why it can diffract around corners. The energy levels of atoms in your wall determine why the signal passes through instead of being absorbed. Now let's talk about interference, because this is where things get genuinely strange in a useful way. Wi-Fi does not travel from your router to your device in a single straight line. It bounces off walls, ceilings, floors, furniture, and your body. It reflects off the metal frame of your window. It diffracts around the corner of a doorway. All of these reflected and diffracted copies of the signal arrive at your device by different paths, each one having traveled a slightly different distance. This means they arrive at slightly different times, and with slightly different phase relationships. Phase means where in the cycle of oscillation, the wave is when it arrives. If two waves arrive perfectly in phase, meaning their peaks and troughs align, they add together and make a stronger signal. This is called constructive interference. If they arrive perfectly out of phase, peaks meeting troughs, they cancel each other out. This is destructive interference. In your home, you have a complicated mixture of hundreds of reflected copies of the signal arriving from different directions. The result is a pattern of stronger and weaker signal levels throughout the space. Spots where the signal is excellent, spots sometimes separated by only a few centimeters where the signal is poor. Wi-Fi engineers know this. Modern Wi-Fi standards, starting with Wi-Fi 4 and increasingly sophisticated in Wi-Fi 6 and Wi-Fi 6E, use a technology called MIMO, which stands for multiple input, multiple output. MIMO uses multiple antennas on both the router and the device. The router can send different versions of the signal from different antennas at different times, deliberately exploiting the multipath environment to steer the signal toward a specific device. This is called beamforming. The router calculates the travel time and phase relationship of signals from each of its antennas to the receiving device and adjusts the timing so that the signals from all antennas arrive in constructive interference at the device. It is using the physics of wave interference, rooted in quantum mechanics at the deepest level, to aim the signal like a spotlight instead of broadcasting it like a lamp. Wi-Fi 6, standardized in 2019 by the IEEE under the specification 802.11 AX, can use up to 8 antennas simultaneously for beamforming. Let's go one level deeper, into the quantum mechanics of the semiconductor itself. When you put silicon atoms together in a crystal, their individual electron energy levels merge into continuous bands of allowed energy. Between bands are gaps, called band gaps, where no electron states exist. In silicon, the band gap is about 1.1 electron volts. This gap is why silicon is a semiconductor. Electrons in the lower energy band, called the valence band, cannot conduct electricity because all the states are full and electrons have nowhere to go. Electrons in the upper band, called the conduction band, can conduct electricity freely, but getting an electron from the valence band to the conduction band requires energy. At room temperature, thermal energy kicks a small number of electrons across the 1.1 electron volt gap. That is enough to make silicon weakly conducting. At very low temperatures, silicon is nearly an insulator. At very high temperatures, too many electrons cross the gap and you lose control of the switching behavior. The transistor takes advantage of this gap. By applying a voltage to a control electrode called the gate, you can shift the energy levels in a thin strip of silicon and either open a channel for electrons to flow from one contact to another or close it. On equals current flowing equals the digit 1. Off equals no current equals the digit 0. Billions of these switches, each one a quantum energy level manipulation, compute every operation your device performs. The energy gap of a semiconductor is also the reason some semiconductors emit light. In a light-emitting diode, electrons drop from the conduction band to the valence band and release their energy as a photon. The color of the photon, meaning its frequency and therefore its energy, equals the band gap energy. Gallium arsenide has a band gap of 1.4 electron volts, which corresponds to infrared light. Gallium nitride has a band gap of 3.4 electron volts, which corresponds to near ultraviolet light. When doped with indium, the band gap shifts into the blue visible range. Blue LEDs based on gallium indium nitride were developed by Shuji Nakamura, Hiroshi Amano, and Isamu Akasaki in the early 1990s. They were awarded the Nobel Prize in Physics in 2014. Their work made efficient white LED lighting possible, which today lights billions of homes worldwide and has dramatically reduced global electricity consumption for lighting. Now consider the photodetector in your phone's camera or the light sensor in your screen's ambient light adjustment. When a photon hits a semiconductor, if the photon energy exceeds the band gap, it can kick an electron from the valence band to the conduction band, creating a free electron in a hole. This is the photovoltaic effect, the same quantum process that makes solar cells work. In a photodetector, this freed electron hole pair is collected as an electrical current. The current is proportional to the number of photons hitting the detector. The number of photons per unit time is the light intensity. Your phone's camera works by counting photons using quantum mechanics in every single pixel of its sensor. The sensor in a smartphone camera contains tens of millions of tiny photodetectors arranged in a grid. Each one is a metal oxide semiconductor device operating on quantum principles. The smallest pixels in modern smartphone sensors, as of 2023, are about 0.8 micrometers across. At this size, the wave nature of light becomes a limiting factor. The wavelength of visible light ranges from roughly 400 to 700 nanometers. At 0.8 micrometers, you are fitting barely one wavelength of red light across a pixel. The optics, the physics of how light bends and focuses, starts to be dominated by diffraction effects that are quantum mechanical in origin. This is why larger pixels in phone camera sensors often produce better low-light images than smaller pixels, even if the smaller pixels give higher resolution in bright light. Everything connects. The wave that comes through your wall is a quantum object. The semiconductor that receives it is governed by quantum energy levels. The transistors that process the signal operate on quantum band gaps. The screen that shows you the result uses quantum electroluminescence. The camera that captures the world for you uses quantum photodetection. You are living inside a quantum device without knowing it. There is one more piece of this that is worth knowing. The reason we can make materials with specific electromagnetic properties, including the materials that make modern Wi-Fi antennae efficient and the materials inside optical cables that carry the internet across continents, comes from our understanding of quantum mechanics. Optical fiber works because engineers can create glass with extremely precise purity and refractive index. Refractive index is how much a material slows and bends light. Optical fiber uses a phenomenon called total internal reflection, where light traveling inside a denser medium hits the boundary with a less dense medium at a shallow angle and cannot escape. It bounces back inside and travels along the fiber. The control of refractive index required to make optical fibers work depends on controlling the quantum mechanical electron structure of the glass. Corning Incorporated, in Painted Post, New York, developed the first optical fiber low enough in loss for practical communication in 1970. William Boyle and George Smith, working at Bell Laboratories in Murray Hill, New Jersey, invented the charge-coupled device in 1969. This became the foundation for all digital imaging. They won the Nobel Prize in Physics in 2009. The technologies that carry the internet under the ocean and the sensors that let you take a photograph are both children of quantum mechanics. And here's the number that puts all of this in perspective. The global internet is carried in large part by light, optical pulses traveling through glass fibers. Each pulse contains roughly a billion photons, 10 to the power of 18, in a nanosecond burst. A nanosecond is 1/billionth of a second. The optical fibers crossing the Atlantic Ocean carry hundreds of terabits of data per second across cables that are thinner than a garden hose over distances of 6,000 kilometers or more. The first transatlantic telegraph cable, laid in 1858 by Cyrus Field and his consortium, could transmit about one character every 2 minutes. The modern fiber cables crossing the same ocean can transmit more data in 1 second than the entire combined text of every book ever written. The advance from then to now is built on Maxwell's equations, Planck's quanta, Einstein's photons, and the quantum band gaps of silicon and gallium arsenide. Your wall does not stop Wi-Fi, because the photons in a Wi-Fi signal are too low in energy to interact with the electron transitions of gypsum, wood, and paint. Your metal pan blocks Wi-Fi, because free electrons in metal absorb photons across a huge range of frequencies. Your body slightly attenuates the signal because the 2.4 gigahertz frequency is absorbed by liquid water. Your chips process the signal because engineers have learned to control quantum energy levels in silicon with extraordinary precision. And the whole system exists because in 1900, Max Planck decided to try an insane mathematical assumption to fix an equation, and it turned out to be true. In 1965, Richard Feynman, one of the great physicists of the 20th century, said in his messenger lectures at Cornell University that nobody understands quantum mechanics. He did not mean that the math does not work. It works with staggering precision. The predictions of quantum electrodynamics, the quantum theory of light and matter, match experiment to more than 10 decimal places. It is the most precisely tested theory in the history of science. What Feynman meant is that human intuition, built for a world of objects you can hold and drop and roll down hills, is not equipped to picture what is actually happening. You cannot visualize a particle with no definite position. You cannot feel a probability cloud. But the math describes it correctly, and the technology built on that math surrounds you entirely. The couch you are sitting on is made of molecules held together by quantum mechanical electron bonds. The light in your room is generated by quantum transitions in LEDs or fluorescent tubes. Your phone is a stack of quantum devices. The signal reaching it passed through your wall because quantum mechanics determined that wall to be transparent at that frequency. You're not just surrounded by quantum effects, you're built from them. In 2012, researchers at the Delft University of Technology in the Netherlands demonstrated quantum entanglement between two electrons separated by 3 meters of distance. In 2015, the same group, led by Ronald Hansen, performed what became known as a loophole-free Bell test, measuring quantum entanglement with sufficient rigor to rule out classical explanations at a distance of 1.3 kilometers. The speed of a classical signal cannot explain how the measurement of one entangled particle instantly appears to influence the measurement of its partner at a distance. Einstein called entanglement spooky action at a distance. He thought it proved quantum mechanics was incomplete. Experiments since 1972 have consistently disagreed. Entanglement is real. It has been used to demonstrate quantum cryptography and is a core feature of quantum computing hardware being developed at IBM, Google, IonQ, and dozens of research universities worldwide. As of 2023, Google's Sycamore quantum processor contained 72 qubits, quantum bits. IBM's Heron processor, released in December 2023, reached 133 qubits. These are not toys. They are early-stage, general-purpose quantum computers, and the processing they perform is fundamentally different from anything a classical transistor can do. The signal is already through the wall. It arrived at your device in less than a millisecond. The waves that carried it were predicted by Maxwell in 1865, explained as packets by Planck in 1900, named photons by Einstein in 1905, and understood in terms of their interaction with atoms by the full development of quantum mechanics between 1925 and 1930. The wall that could not stop the signal was seen through by a chain of thought that ran through the minds of Planck, Einstein, Bohr, de Broglie, Schrödinger, Heisenberg, Dirac, and Feynman over a span of 60 years. Every engineer who designed the chip in your phone, every physicist who measured the band gap of silicon, every materials scientist who made the glass pure enough to carry light across an ocean was using tools built from that chain of thought. And the signal still travels through your wall every second of every day, asking nothing of you, requiring no understanding from you to work. But it is built on the most profound and strange and verified description of reality that human beings have ever produced. The wall never stood a chance. Consider the frequencies that did not make it. Gamma rays and X-rays pass through soft tissue but are blocked by dense bone and metal. That is why X-ray imaging works. A chest X-ray taken at a hospital uses photons with wavelengths of around 0.1 nanometers and energies of around 10,000 electron volts. Those photons pass through soft tissue because the electron structures of soft tissue atoms do not have matching transition energies at that frequency. Dense bone contains calcium phosphate, which has a higher density of electrons that do interact with X-ray photons. So bone absorbs more X-ray photons and appears white on the image. The image is a quantum shadow, a map of which atoms absorbed photons and which allowed them through. Every medical X-ray you have ever had was produced using the same quantum principle that lets your Wi-Fi pass through drywall. Different frequencies, different materials, same physics. Ultraviolet light, with wavelengths between 10 and 400 nanometers and energies between 3 and 124 electron volts, is blocked by standard glass. That is why a sunny window does not give you a sunburn the way direct sun does. Glass is transparent to visible light, but absorbs ultraviolet. The silicon-oxygen bonds in glass have electron transitions that match ultraviolet photon energies. UV photons get absorbed before they pass through. Special UV transparent glass exists, made from materials like fused silica or quartz, which have different electron structures. Fused silica windows are used in scientific instruments and in some germicidal UV systems. But your home window glass keeps UV out by the same mechanism that keeps visible light out of your wall. Infrared light, with wavelengths from 700 nanometers to 1 millimeter, falls between visible light and microwaves. Near infrared, from about 700 to about 2,500 nanometers, passes through silicon. This is why silicon chips can be inspected from the backside using infrared cameras. Engineers can see through the silicon substrate to the transistor structures on the other side because silicon is transparent at those wavelengths. The electron band gap of silicon, 1.1 electron volts, corresponds to photons with wavelengths longer than about 1100 nanometers. Any photon with longer wavelength carries less energy than the band gap and passes through without being absorbed. Any photon with shorter wavelength carries enough energy to kick an electron across the gap and gets absorbed. This is the exact same quantum logic every time. The frequency of the light determines the energy per photon. The energy per photon compared to the electron transition energies of the material determines whether the photon is absorbed or transmitted. Your television remote control uses infrared light at wavelengths around 900 nanometers. It passes right through the silicon photodetector in the front of your television set because the silicon is transparent at that wavelength. Wait, if silicon is transparent to 900 nanometer infrared, how does the photodetector in the TV pick it up? The answer is doping. The silicon in the photodetector is doped to create impurity levels inside the bandgap. These impurity levels can absorb photons at energies lower than the full bandgap. Doped silicon has additional electron transitions engineered specifically to detect infrared. This is another quantum engineering triumph. By adding atoms of a different element, engineers shift where the material absorbs light. This same trick is used in photodetectors across the spectrum, from the visible sensors in your smartphone camera to the infrared sensors in military night vision equipment to the near-infrared sensors and fiber optic communication systems. The fiber optic system that carries most of the internet's data across continents operates at wavelengths around 1550 nanometers in the infrared. This wavelength is chosen deliberately. It is the wavelength at which pure silica glass fiber has its lowest loss. Photons at this frequency travel farther through fiber before being absorbed or scattered than photons at any other frequency. The minimum loss in silica fiber at this wavelength is about 0.2 decibels per kilometer. Over a 6,000 kilometer transatlantic cable that still adds up to enormous loss, which is why optical amplifiers are placed along the cable at intervals of roughly 80 kilometers. These amplifiers use a section of fiber doped with erbium, a rare earth element. When pumped with a laser at a shorter wavelength, the erbium atoms are excited to a higher energy level. When a signal photon at 1550 nanometers passes through, it stimulates the erbium atoms to emit additional photons at the same wavelength and in the same direction. This is stimulated emission, the same quantum process that Albert Einstein described mathematically in 1917 and that Theodore Maiman used in 1960 to build the first laser. The Internet's backbone amplifiers are lasers. The Internet runs on quantum mechanics.